What if black holes had cosmic twins, mirror images that defy everything we know about the fabric of space and time? Picture this: a region of the universe where matter and light don't disappear into darkness but explode outward, where the laws of physics seem to reverse themselves, and where the very idea of an exit becomes possible. These aren't just wild speculations, they're white holes, the enigmatic theoretical counterparts to black holes, and they might just hold the keys to some of the universe's most profound mysteries. While black holes suck everything in, never to escape, white holes, if they exist, would do the exact opposite, spewing out energy and matter like cosmic fountains. But here's the catch: no one has ever seen one. No direct evidence, no smoking gun, just equations on a page and a universe full of questions. So why do scientists keep coming back to the idea of white holes? Because they could rewrite our understanding of reality itself. Imagine a universe where black holes and white holes are two sides of the same coin, where wormholes bridge distant corners of space-time, and where the Big Bang itself might have been the ultimate white hole event. The possibilities are as breathtaking as they are bizarre. Today, we're diving deep into 25 mind-bending theories about white holes, why they might exist, where they could be hiding, and how they could change everything we know about the cosmos. From Einstein's equations to cutting-edge quantum gravity, from the edges of known physics to the wild frontiers of speculation, we'll explore the ideas that make white holes one of the most tantalizing mysteries in all of science. This isn't just about abstract theories, it's about the very nature of existence. What if white holes are the missing pieces in the puzzle of dark matter? Could they be the secret engines behind some of the universe's most energetic explosions? Or are they nothing more than mathematical ghosts, beautiful ideas that vanish under the harsh light of reality? Buckle up, because we're about to journey through the looking glass into a world where time flows backward, where universes might be born from singularities, and where the line between science and science fiction blurs into something extraordinary. By the end, you might just see the cosmos and your place in it in a whole new light. One of the most striking theories about white holes suggests they might not be separate objects at all, but black holes playing the cosmic tape in reverse. Think about a black hole's defining feature, its relentless pull dragging everything past the point of no return. Now flip that image. Instead of matter vanishing into oblivion, picture it bursting back out, not falling inward, but exploding outward as if time itself had switched direction. This isn't just a thought experiment, it's a direct consequence of Einstein's equations, which describe gravity as the curvature of space-time. Mathematically, those equations are symmetrical. They don't care whether time runs forward or backward. Plug in the numbers one way and you get a black hole. Reverse the flow and suddenly you're describing a white hole. The idea gained traction in the 1960s when physicists like Igor Novikov began seriously considering the implications. If white holes are time-reversed black holes, they'd still obey the same fundamental rules, just in mirror image. A black hole's event horizon, the boundary where nothing escapes, would become a white hole's anti-horizon, a barrier where nothing can enter. Matter and energy wouldn't disappear, they'd erupt like a cosmic replay button hit at the moment of collapse. But here's where things get tricky. While the math allows it, nature might not. Black holes form from dying stars, their collapse driven by overwhelming gravity. A white hole in this scenario would need to uncollapse, reversing entropy itself, something thermodynamics says is nearly impossible without adding absurd amounts of energy. Yet the theory refuses to fade. Some researchers argue that white holes could exist briefly as black holes transition between states in the quantum realm. Others suggest they might be hiding in plain sight, masquerading as unexplained cosmic explosions. And then there's the wildest possibility of all, that every black hole's death gives birth to a white hole in another universe, stitching together realities through a singularity. Whether these ideas hold up or not, they force us to confront deep questions. If time symmetry is baked into physics, why does the universe seem to prefer one direction? Could causality ever truly run backward? For now, white holes remain a tantalizing what if, a reminder that even our most elegant equations might only be half the story. The time reversal model of white holes presents an elegant symmetry, but physics is rarely so forgiving. One major obstacle is thermodynamics, specifically the relentless march of entropy, often called the arrow of time. In our universe, disorder always increases. A shattered glass doesn't reassemble, smoke doesn't retreat back into a fire. So how could a black hole, having devoured stars and galaxies, suddenly reverse course and spit everything out intact? The math might allow it, but nature seems to scoff at the idea. Critics argue that even if Einstein's equations permit white holes, thermodynamics slams the door shut. Entropy isn't just a suggestion, it's a cosmic rulebook, and reversing it would require rewriting the very fabric of reality. Then there's the problem of causation. If a white hole is a black hole running backward, does that mean effects could precede causes? Imagine a supernova erupting before the star collapses, or light traveling back into a flashlight. Such violations of causality make physicists deeply uneasy. The universe as we know it operates on a strict cause and effect sequence, what scientists call local realism. White holes in their purest form threaten to unravel that principle. Some researchers dismiss them outright for this reason, arguing they're mathematical curiosities with no physical counterpart. But hold on, what if quantum gravity steps in to bridge the gap? Here's where the debate gets fascinating. At the tiniest scales where quantum mechanics dominates, the rules soften. Particles tunnel through barriers they shouldn't cross. Electrons exist in multiple states at once. Could white holes be quantum flukes, flickering into existence just long enough to release trapped energy before vanishing? Loop quantum gravity, a leading theory marrying quantum mechanics with relativity, suggests that black holes might avoid infinite collapse, rebounding as white holes instead. In this scenario, the transition wouldn't violate thermodynamics. It would sidestep it entirely, like a cosmic sleight of hand. Another twist comes from the holographic principle, which posits that the information swallowed by a black hole isn't lost but encoded on its surface. If that's true, a white hole could be nature's way of playing back that information, like a projector reconstructing a burned film. The catch: this process would take unimaginable timescales, far longer than the current age of the universe. So while the theory might solve the entropy problem, it leaves white holes feeling more like philosophical musings than observable phenomena. The controversy highlights a deeper tension in physics between the pristine symmetry of equations and the messy reality they describe. Maybe white holes aren't forbidden, just hidden, waiting for the right conditions or a new framework to make sense of them. Or perhaps they're signposts pointing toward a grander theory we haven't yet grasped. Either way, the debate isn't just about hypothetical objects. It's about understanding whether the universe cares more about elegance or practicality, and whether our current laws are the final word or just the beginning. What if the birth of our universe wasn't a singular explosion from nothing, but the aftermath of something even more extraordinary? Picture the Big Bang not as the beginning of everything, but as the explosive finale of a previous cosmic era. Some physicists propose that the Big Bang was actually a white hole event, a colossal eruption of matter and energy from a singularity. This radical idea flips our origin story on its head. Instead of emerging from an infinitely dense point, our universe might have been forged in the fiery outburst of a white hole, a cosmic reset button pressed by the collapse of another reality. The theory finds surprising support in loop quantum gravity, where the concept of a quantum bounce offers an elegant alternative to the traditional Big Bang model. According to physicists like Carlo Rovelli, when a collapsing universe reaches extreme densities, quantum effects could reverse its implosion into an explosion, just like a stretched spring snapping back. Think of it as cosmic recycling. A dying universe contracts into a singularity, only to rebound as a white hole, birthing a new spacetime in the process. The equations suggest that under these conditions, gravity becomes repulsive rather than attractive, turning collapse into creation. This isn't pure speculation. A quantum bounce model solves several nagging problems with the classical Big Bang theory. For one, it avoids the need for a true singularity, a point of infinite density where physics breaks down entirely. Instead, the bounce acts like a quantum trampoline, giving spacetime a finite minimum size. It also provides a natural explanation for the universe's eerie uniformity. The violent stretching during the bounce's rebound could have ironed out irregularities, explaining why the cosmic microwave background appears so smooth. But how would this white hole origin differ from the standard Big Bang? Imagine the difference between a firecracker exploding in empty space versus a geyser erupting from an underground reservoir. In the white hole scenario, the energy of our universe didn't appear from nothing. It was transformed, recycled from a prior state. Some models even suggest that information from the previous universe could imprint itself on the new one, like shadows on a reborn cosmos. The implications are staggering. If correct, our universe may be just one link in an endless chain of cosmic resurrections, each Big Bang heralding both an end and a beginning. It raises profound questions. Could traces of the previous universe survive in ours? Might black holes in our sky eventually seed new realities elsewhere? While we lack definitive proof, the white hole Big Bang theory offers something perhaps more valuable, a glimpse of how the ultimate cosmic mystery might fit into a larger, more magnificent pattern. The universe's origin story may not be a single act of creation, but an eternal rhythm of collapse and rebirth, with white holes as the universe's beating heart. If black holes can evaporate, as Stephen Hawking famously theorized, where does all that trapped energy and information go? Enter quantum gravity, where the rules get rewritten at the tiniest scales. In this realm, white holes aren't just mathematical oddities, they might be cosmic inevitabilities. Loop quantum gravity, a leading framework blending relativity with quantum mechanics, suggests that when black holes reach the end of their life cycles, they don't vanish into nothingness. Instead, they could rebound as white holes, leaving behind remnants so dense and strange they defy classical physics. At the heart of this idea lies the Planck star, a theoretical object proposed by physicists like Carlo Rovelli. Picture a black hole collapsing not into a dimensionless singularity, but halting at a point where quantum effects take over. At this scale, around 10 to the minus 35 meters, space-time becomes granular like pixels on a screen. Gravity flips from crushing inward to pushing outward, triggering a cosmic U-turn. The dying black hole doesn't just fizzle out, it erupts, transforming into a white hole in a process that could take billions of years, or happen in a flash depending on the observer's frame of reference. Abhay Ashtekar and his collaborators have pushed this even further. Their models show how the fabric of space-time, when stretched to its quantum limits, behaves more like a woven tapestry than a smooth sheet. Tiny loops in this fabric could prevent singularities from forming altogether, replacing the infinite density of a black hole's core with a dense but finite knot of energy. When this knot unravels, it doesn't just release Hawking radiation, it might unleash a white hole's explosive rebirth. The implications are staggering. If correct, every black hole in our universe could eventually become a white hole, turning the cosmos into a network of dormant time bombs waiting to detonate. Some theories even suggest gamma-ray bursts, some of the most energetic events ever observed, could be the signatures of ancient black holes finally rebounding. But here's the catch. These white holes would operate on timescales alien to human experience. From outside, a collapsing star might appear frozen as a black hole for eons before its white hole phase becomes visible. From inside, the transition could feel instantaneous, like a tunnel snapping inside out. This dance between quantum mechanics and gravity doesn't just rescue information from oblivion, it reshapes how we view the universe's life cycle. If black holes carry the seeds of white holes within them, then death and rebirth might be woven into the cosmos at the most fundamental level. The Planck star concept offers more than an escape from singularities. It hints at a universe where even the most voracious voids have an expiration date, and where every end might just be a new beginning in disguise. What if the universe's most elusive substance, dark matter, isn't made of exotic particles at all, but something far stranger? Imagine white holes, those theoretical cosmic fountains, lurking unseen throughout galaxies, their gravity warping space in ways that mimic dark matter's elusive pull. This radical idea turns conventional astrophysics on its head. While most searches for dark matter focus on hypothetical particles like WIMP or actions, a handful of physicists dare to ask, could the answer lie in the explosive remnants of white holes instead? The math is tantalizing. Dark matter's presence is inferred through its gravitational grip, the way it bends light around galaxies and keeps stars from flying apart. White holes, if they exist in abundance, could produce similar effects. Unlike black holes, which devour everything, white holes would exert gravity without absorbing nearby matter. Their sheer mass, locked in dense remnants from the early universe, might create the invisible scaffolding that holds galaxies together. Picture a cosmos peppered with dormant white holes, relics of a violent past, their gravitational footprints masquerading as dark matter's influence. But the theory faces glaring challenges. For one, white holes are expected to erupt energy, not sit quietly. If they were spewing radiation, we'd likely detect their outbursts. Proponents counter that ancient white holes could have exhausted their energy, settling into stable, inactive states, cosmic cinders still bending space but no longer flaring. Others suggest quantum effects might trap them in a near-permanent state of suspended animation, like a firework frozen mid-explosion. Observationally, the hurdles multiply. Dark matter appears smoothly distributed, whereas white holes would be discrete objects. To match observations, they'd need to be absurdly dense and numerous, packed tighter than stars but smaller than atoms. Even then, their gravity might clump differently than dark matter's seamless halo. Some models tweak the idea, proposing microscopic primordial white holes forged in the Big Bang's chaos. These could evade detection while collectively mimicking dark matter's pull. The strongest critique: we've never seen a white hole, let alone proven they exist. Without direct evidence, the theory leans heavily on speculation. Yet it refuses to die, partly because it offers a wild but elegant solution to two mysteries at once. If correct, white holes wouldn't just be cosmic oddities. They'd be the hidden architects of the universe's structure, the unseen hands guiding galaxies into shape. Until we find them, or rule them out, the possibility lingers, a ghost in the equations of gravity, whispering that the universe's darkest secret might be written in the language of white holes. What if white holes aren't just cosmic anomalies in our universe, but gateways to entirely different realities? The wildest theories in physics suggest these mysterious objects could be threaded through the fabric of space-time like cosmic stitches, connecting our universe to others in a vast multiverse. At the heart of this idea lies the concept of wormholes, hypothetical tunnels through space-time, often depicted as shortcuts between distant points. But here's where it gets mind-bending. Some models propose that a white hole might be one end of a wormhole, with a black hole serving as the other. Picture a cosmic pipeline where matter vanishes into a black hole in one universe only to erupt from a white hole in another, a one-way trip between realities. This isn't just science fiction. The mathematics of general relativity actually allows for such structures, dubbed Einstein-Rosen bridges. The catch: Traditional wormholes would collapse instantly under their own gravity, pinching shut before anything could traverse them. That's where quantum mechanics and string theory enter the fray. Leonard Susskind and others have explored the ER equals EPR conjecture, a daring proposal linking wormholes Einstein-Rosen or ER to quantum entanglement Einstein-Podolsky-Rosen or EPR. In this framework, entangled particles might be connected by microscopic wormholes, implying that the fabric of space itself could be woven from these hidden threads. String theory takes it further, suggesting that white holes could anchor these bridges in higher dimensional space. Imagine our four-dimensional universe as a membrane floating in a higher dimensional bulk. A white hole in our universe might puncture this membrane, its energy bleeding into another brane, another universe elsewhere in the bulk. This could explain why white holes seem conspicuously absent in our cosmos. They're not missing, they're just venting into other dimensions. The implications ripple through multiverse theories. If white holes act as cosmic spillways, they could solve one of the biggest puzzles in cosmology: what happened before the Big Bang? Some models suggest our universe's violent birth was triggered by a white hole in a parent universe, funneling matter and energy into our fledgling reality. Others propose that every black hole in our universe births a new cosmos through its white hole counterpart, creating an infinite tree of branching universes, each with its own laws of physics. Critics argue that without empirical evidence, these ideas remain speculative. Yet they offer a breathtaking vision: white holes as more than mathematical curiosities, but as the connective tissue of a multiverse, weaving together realities in a tapestry far grander than we've dared to imagine. Whether they are out there or not, the mere possibility stretches the limits of our understanding, reminding us that the universe or universes might be stranger than we ever dreamed. Stephen Hawking once turned the notion of white holes on its head by proposing they might not be massive cosmic gushers at all, but microscopic relics of the Big Bang itself. Imagine the early universe as a bubbling quantum soup, where space-time churned with such violent energy that tiny pockets of reality could flip inside out. In this primordial chaos, Hawking theorized fleeting white holes might have flickered into existence, each one a miniature Big Bang in reverse. These wouldn't be the colossal structures we've imagined before, but quantum-scale anomalies smaller than atoms and vanishing almost instantly. The mechanism hinges on a phenomenon called quantum fluctuation. Even in a vacuum, space isn't truly empty. It crackles with virtual particles that pop in and out of existence, borrowing energy from the void before vanishing again. In the extreme conditions of the early universe, Hawking suggested, these fluctuations could have birthed microscopic white holes. Picture a bubble of space-time pinching off from the main fabric, its gravity inverting for a split second before collapsing back into the cosmic backdrop. These wouldn't be stable objects like stars or planets, but quantum hiccups here one moment, gone the next. But why wouldn't they last? The same force that might create them, quantum instability, would also spell their doom. A primordial white hole would face relentless pressure from the surrounding universe. Unlike their hypothetical massive counterparts, these tiny versions wouldn't have the gravitational muscle to resist disintegration. Instead of spewing matter outward for eons, they'd implode almost immediately, their energy dissipating like a soap bubble bursting in the wind. Hawking even speculated that their demise might resemble his famous radiation, the same process that causes black holes to slowly evaporate. In this case, though, the radiation wouldn't leak out over millennia. It would erupt in a sudden, tiny flash, vanishing without a trace. The implications ripple through modern cosmology. If primordial white holes existed, they could have seeded the universe with exotic energy distributions, leaving faint imprints in the cosmic microwave background. Some theorists suggest they might even explain certain high-energy cosmic rays particles with energies so extreme, no known astrophysical process can account for them. Could these be the last echoes of white holes that blinked out 13 billion years ago? Hawking's hypothesis bridges two seemingly irreconcilable worlds, the quantum and the cosmic. It suggests that white holes aren't just the stuff of abstract equations, they might have been real, if ephemeral, players in the universe's opening act. While we've yet to find concrete evidence, the idea lingers as a tantalizing what if, reminding us that the smallest phenomena can sometimes cast the longest shadows across the cosmos. Gamma-ray bursts are among the most violent events in the cosmos, blasts of energy so intense they outshine entire galaxies for brief moments. For decades, astronomers have struggled to explain what could possibly unleash such staggering power. But one audacious theory suggests these cosmic fireworks might not come from collapsing stars or colliding neutron stars, but from white holes erupting into existence. The logic is startlingly simple. If white holes truly exist, they'd release pent-up energy in catastrophic outbursts. Picture a black hole that spent billions of years devouring matter, only to rebound as a white hole in its final moments. All that trapped mass and radiation would explode outward in a concentrated beam, precisely the signature we see in gamma-ray bursts. Some models even suggest these eruptions could last mere seconds, matching the ultra-short bursts we've detected across the universe. But here's where things get interesting. Not all gamma-ray bursts look the same. Some are brief and intense, while others smolder for minutes. White holes might neatly explain the short bursts, those sudden, brilliant flashes, but the longer events pose a problem. If a white hole eruption were truly instantaneous, where would the sustained energy come from? Proponents counter that quantum effects could stretch the explosion from our perspective, like watching a strobe light through frosted glass. Time dilation near the event horizon might make a split-second eruption appear to linger. Another clue lies in the burst's afterglows, the fading X-ray and radio emissions that linger for days. White hole models struggle to account for these, as they'd likely expend all their energy in one dramatic pulse. Compare that to neutron star collisions, which naturally produce lingering debris fields. Still, some theorists propose that white holes could leave behind exotic remnants, Planck scale, ash from their quantum fire, that might emit secondary radiation mimicking an afterglow. The biggest hurdle, directionality. Gamma-ray bursts fire focused jets, not omnidirectional explosions. For a white hole to match this, its eruption would need to be funneled, perhaps by an inherited spin from its black hole predecessor. And then there's the question of frequency. If every dying black hole becomes a white hole, why don't we see more gamma-ray bursts? Perhaps most rebound too slowly or too dimly, or maybe we're just catching the rare, spectacular ones. While the theory remains speculative, it offers a mesmerizing possibility that the universe's most energetic explosions aren't endings at all, but cosmic rebirths, white holes screaming into existence across the void. Until we catch one in the act, though, these titanic bursts will keep their secrets, leaving us to wonder whether we're witnessing stellar death or something far stranger. The holographic principle turns our understanding of reality inside out, literally. It suggests that our three-dimensional universe might be a projection from information encoded on a two-dimensional surface, like a cosmic DVD encoding an entire movie on its flat face. So where do white holes fit into this mind-bending framework? If the holographic principle holds, then white holes wouldn't just be exotic objects in space, they'd be glitches in the universe's underlying code, moments where the projected reality fractures and reveals something deeper beneath. At the heart of this idea lies the AD/CFT correspondence, a groundbreaking concept in string theory that mathematically links theories of gravity in higher dimensions to quantum field theories on lower dimensional boundaries. Think of it like this: a black hole's event horizon isn't just a point of no return, it's a screen where all the information swallowed by the black hole gets stored pixel by pixel. Now reverse the process. A white hole's eruption wouldn't just be matter exploding into space. It'd be information cascading off that holographic boundary, like a movie playing in reverse but still making perfect sense. Juan Maldacner's work on anti-de Sitter space ADS suggests something startling. If a black hole's interior is described by physics in bulk space, then its surface, the event horizon, obeys a completely different set of rules described by conformal field theory (CFT). Apply this to white holes and you get a tantalizing possibility. Their explosive outputs might not be random but perfectly decoded information, meticulously reconstructed from the holographic surface. It's as if the universe keeps flawless backups, ensuring nothing ever truly vanishes, just gets temporarily stored in cosmic cold storage. This gets even stranger when you consider firewall paradoxes. Quantum mechanics demands that information can't be destroyed, yet black holes seem to erase it. The holographic principle offers an escape hatch. The information isn't lost, it's scrambled onto the event horizon. A white hole, then, could be nature's decoder ring, spitting that scrambled data back out in readable form. Leonard Suskind's work on black hole complementarity takes it further, suggesting that from an outside observer's perspective, matter never actually crosses the horizon, it smears onto it, while from the infaller's view they plunge right through. A white hole might reconcile these views, acting as the endpoint where the hologram's duality collapses back into unity. Critics argue this stretches the holographic principle beyond its tested limits. After all, ADS/CFT works neatly in idealized mathematical universes, not necessarily our messy, expanding cosmos. But supporters counter that if white holes exist, they'd provide the ultimate test case, a natural laboratory where holography's predictions could manifest spectacularly. Imagine detecting a white hole eruption and finding its energy spectrum matches a perfect information unscrambling sequence. That wouldn't just confirm white holes, it'd prove the universe itself is a hologram. The implications ripple through physics. If white holes preserve and project holographic information, they might hold keys to quantum gravity's grand unification. They could explain how the universe preserves causality across singularities, or how entanglement might weave space-time itself. Or they might force us to ask an even deeper question. If reality is a projection, what's projecting it? And could white holes be the universe's way of editing the script on the fly? For now, these questions hover at the edge of theory and observation, where mathematics and metaphysics blur into something extraordinary. One thing's certain: if the holographic principle is right, then white holes aren't cosmic accidents, they're inevitable features in the universe's grand code waiting to be debugged. Einstein's theory of general relativity isn't the only game in town when it comes to explaining gravity, and some of its alternatives might make white holes far more than mathematical oddities. Take F of R gravity, a class of modified gravity theories where the fabric of space-time responds to curvature in radically different ways. Here, the equations don't just permit white holes, they practically demand them. Unlike general relativity, where white holes are symmetrical curiosities, these frameworks suggest they could be inevitable cosmic players woven into the universe's structure from the beginning. At the core of F of R gravity lies a simple but profound tweak. Instead of gravity being purely governed by the curvature of space-time, it also depends on higher-order terms, mathematical additions that kick in under extreme conditions. Picture a spring that stiffens the harder you pull it. In these models, when space-time bends beyond a critical threshold, the rules shift and gravity can flip from pulling inward to pushing outward. That's where white holes enter the picture. In some scenarios, a collapsing star wouldn't just form a black hole, it would rebound, its implosion halted and reversed by these repulsive forces, birthing a white hole in a cosmic bounce. The implications ripple through cosmology. If modified gravity is correct, white holes might not be rare freaks of nature but commonplace features, especially in the early universe. Some theories even suggest that the Big Bang itself could have been a supermassive white hole event, propelled by these repulsive gravitational effects. Compare that to general relativity, where white holes are optional extras mathematically possible but physically dubious. In F of R gravity, they're front and center potential linchpins in how the universe evolves. But how could we test these bold claims? One clue lies in gravitational waves. When black holes collide, they send ripples through space-time, and the signals we detect match Einstein's predictions nearly perfectly. However, if white holes exist and erupt, they'd produce their own distinct wave patterns, bursts of high-frequency vibrations unlike anything black holes generate. Future detectors like the Laser Interferometer Space Antenna, or LISA, might catch these whispers from the void. Another smoking gun could lurk in the cosmic microwave background. If primordial white holes peppered the infant universe, their explosions might have left faint scars in this ancient light, imprints waiting to be decoded. Critics argue that modified gravity theories often struggle to explain phenomena as elegantly as general relativity. For instance, they can't yet account for the precise orbits of Mercury or the bending of light around galaxies without introducing ad hoc fixes. But supporters counter that white holes might be the missing piece, evidence that gravity's true nature reveals itself only at the edges of our understanding. Whether these theories hold up or not, they force us to confront a thrilling possibility: that white holes aren't just ghosts in Einstein's equations, but vital clues pointing toward a deeper, richer theory of everything. The universe's most enigmatic objects might be hiding in plain sight, not because they're rare, but because we've been looking with the wrong set of rules. One of the most perplexing puzzles in modern physics isn't about what black holes destroy, but what they might secretly preserve. The black hole firewall paradox, first articulated by Olmary, Marolf, Polchinski, and Sully, collectively known as AMPS, throws a wrench into our understanding of quantum mechanics and general relativity. At its core, the paradox asks a brutal question: what happens to information that falls into a black hole? Quantum mechanics insists it can't be destroyed, yet relativity suggests it's erased past the event horizon. To reconcile this, AMPS proposed an unsettling solution: a blazing wall of energy just inside the horizon, incinerating anything that crosses it. But this firewall creates more problems than it solves, violating Einstein's equivalence principle, which states free fall should feel like floating in empty space. Enter white holes, flipped counterparts to black holes that might not just resolve this paradox but turn it inside out. If black holes and white holes are quantum-entangled partners, as some theories suggest, then information swallowed by a black hole wouldn't need to be destroyed or trapped behind a firewall. Instead, it could be teleported, emerging unscathed from a connected white hole. Picture this: a black hole's event horizon isn't a one-way street to oblivion, but one end of a cosmic relay race where information gets handed off to a white hole waiting in the wings. The firewall wouldn't be a destructive barrier but a transfer point, a brief quantum handshake between entangled singularities. The math behind this idea ties into the ER=EPR conjecture, which links wormholes' Einstein-Rosen bridges to quantum entanglement, Einstein-Podolsky-Rosen correlations. In this framework, every particle falling into a black hole remains subtly connected to its mirror twin racing outward from a white hole. No information is lost, it's just rerouted like mail sent through an interdimensional post office. This wouldn't just protect quantum mechanics' sacred rule against information loss. It'd also preserve the smoothness of space-time near the horizon, eliminating the need for a violent firewall. Critics argue this sounds like sleight of hand, replacing one paradox with another. If white holes are the answer, where's the observational proof? Supporters counter that subtle signatures might lurk in the Hawking radiation of evaporating black holes, encoded in delicate quantum correlations. Others suggest that gamma-ray bursts or even anomalies in the cosmic microwave background could bear the fingerprints of white hole eruptions if we know how to look. The firewall paradox forces us to confront a deeper truth. The universe abhors information loss as much as it abhors a vacuum. Whether through firewalls, white holes, or some yet undiscovered mechanism, reality seems determined to preserve its data, even if that means bending the rules of space and time to do it. In this light, white holes aren't just cosmic curiosities. They're potential keystones holding together the fragile marriage of quantum theory and gravity, ensuring that no bit of information, no matter how small, ever truly disappears. What if space-time isn't smooth and continuous like a sheet of fabric, but more like a granular mosaic built from tiny, indivisible chunks? Causal set theory proposes exactly that, a radical reimagining of the universe where time and space emerge from a vast network of discrete events linked by cause and effect. In this framework, the elegant continuum of Einstein's relativity gives way to something starker, a cosmic scaffold where every connection matters and where white holes might not be anomalies but inevitable twists in the web of causality itself. At the heart of this idea lies a simple but profound shift. Instead of treating space-time as a fluid backdrop, causal set theory treats it as a collection of point-like events, each tied to others by a strict order of before and after. Picture a sprawling family tree where every node represents a moment in the universe's history, and every line traces the unbreakable chain of cause and effect. In this universe, singularities, those infinitely dense points at the cores of black holes, don't exist. Instead, the crushing density of collapse hits a fundamental limit, like sand grains resisting further compression. When that limit is reached, something extraordinary happens. The causal structure flips and a white hole blossoms from the rubble. This isn't just mathematical sleight of hand. By avoiding singularities, causal set theory sidesteps the breakdown of physics that plagues traditional models. In general relativity, singularities are where equations explode into nonsense, places where gravity becomes infinite and predictability vanishes. But in a causal set, the granularity of space-time acts like a cosmic safety net, preventing infinite collapse. A black hole's implosion would halt at the smallest possible scale, then rebound as a white hole, not because of repulsive gravity or quantum effects, but because the underlying causal links simply can't be crushed any further. The implications ripple through our understanding of white holes. Unlike continuum theories where white holes feel tacked on as time-reversed oddities, causal set theory treats them as natural outcomes of the universe's discrete architecture. They're not glitches, they're features emerging from the deep structure of reality like knots in a net. Some models even suggest these white holes would be quiet, lacking the violent eruptions predicted elsewhere because their birth isn't driven by pent-up energy but by a rearrangement of causal relationships. Critics argue that without experimental evidence, causal set theory remains speculative. Yet it offers something priceless, a universe where white holes aren't just possible but unavoidable. If space-time is truly granular, then every black hole's fate might be written in the immutable ledger of cause and effect, its collapse turning into an outpouring not by choice, but by the universe's deepest architectural rules. Whether this vision holds up or not, it forces us to confront a tantalizing question. Are white holes the universe's way of respecting its own causal limits, ensuring that no event, no matter how extreme, ever truly breaks the chain of before and after? In a cosmos built from cause and effect, the answer might be as simple as counting the links. Stephen Hawking left us with a cosmic riddle that still keeps physicists up at night. If black holes evaporate, what happens to all the information they swallow? Quantum mechanics insists that information can never be destroyed. It might get scrambled, but it must persist. Yet black holes seem to violate this sacred rule, consuming stars, planets, and even light without leaving a trace. This is the information paradox, a glaring contradiction between quantum theory and relativity that's fueled decades of debate. But hidden in the equations might lie an elegant solution. One where white holes don't just rescue lost information, but birth entirely new universes to preserve it. The paradox starts with Hawking radiation. As black holes slowly leak energy, they should eventually vanish, taking all that swallowed information with them. That's a problem because quantum mechanics treats information like indestructible building blocks. Erase them, and the entire framework collapses. Enter white holes. Some theorists propose that when a black hole dies, it doesn't just fizzle out. Instead, it rebounds as a white hole, vomiting back all that trapped information in a final burst. It's as if the universe has a failsafe. When one door closes, another flings open to keep the cosmic ledger balanced. But here's where it gets wild. What if that information doesn't just return to our universe? Lee Smollen's baby universe theory suggests something far grander, that every black hole collapse spawns an entirely new cosmos inside its remnants, with the swallowed information reincarnated as the seed of a fresh reality. Picture a Russian nesting doll of universes, each born from the singularity of a parent universe's black hole, its physical laws subtly tweaked in the process. In this scenario, white holes aren't just cosmic recycling plants. They're umbilical cords tethering us to countless offspring universes, each carrying forward the information we thought was lost. Critics pounce on two glaring issues. First, baby universes are fundamentally unobservable if they exist beyond our space-time. We'd never detect them, making the theory untestable. Second, even if information escapes into a new universe, it's effectively gone from ours, which doesn't solve the original paradox. It's like claiming a burned book isn't lost because its ashes fertilized a tree that grew new paper. Technically true, but cold comfort to anyone trying to read the original text. Yet the theory persists, buoyed by its sheer audacity. It offers a sweeping vision where white holes aren't endpoints, but create as cosmic midwives presiding over the birth of new realities. Even if we can't see these baby universes directly, their potential existence reshapes how we think about information, causality, and the very nature of existence. Perhaps the universe's most precious data isn't meant to be retrieved but repurposed, woven into the fabric of realities we'll never see. Whether this answers Hawking's paradox or just kicks the can down the road, one thing's certain. In a cosmos where black holes gulp and white holes spew, information might be the one thing that never truly disappears. It just changes address. Roger Penrose's cosmic censorship conjecture is like the universe's strictest bouncer. It insists that every singularity must stay hidden behind an event horizon, never exposing its infinite weirdness to the outside world. Black holes obey this rule perfectly, wrapping their singularities in darkness, but white holes, they're the cosmic rule breakers, potentially flinging naked singularities into plain view points of infinite density without any event horizon to shield us from their chaos. If they exist, these uncloaked singularities wouldn't just challenge Penrose's conjecture, they'd tear up the rulebook of predictability itself. Imagine a singularity sitting out in the open, warping space and time with no horizon to contain its influence. The equations of general relativity crumble here. Gravity becomes unpredictable, bending light in ways that defy logic and causality. The unbreakable chain of cause and effect starts to fray. Need an example? Picture a spaceship orbiting a naked singularity. Normally, the well-defined event horizon of a black hole sets clear boundaries for what's survivable. But without that horizon, the ship could spiral into regions where time loops back on itself or where gravity switches directions mid-flight. Physics as we know it would lose all meaning. The debate over naked singularities splits physicists into two camps. Traditionalists argue that nature abhors such lawlessness, that cosmic censorship must hold, and white holes either don't exist or somehow dress their singularities in horizons at the last moment. Yet proponents of radical theories counter that the universe might not be so tidy. Numerical simulations of collapsing stars occasionally spit out naked singularities, suggesting they're mathematically possible even if taboo. If white holes erupt from black hole rebounds, could they briefly expose a naked singularity before settling into stability? The answer could redefine how we understand the universe's tolerance for chaos. Observationally, the stakes are sky high. A naked singularity would be the ultimate cosmic spectacle, distorting light so severely that it might create multiple, overlapping images of distant galaxies, like a funhouse mirror for the entire universe. Some astronomers even speculate that certain ultra-high-energy cosmic rays could be signatures of these unruly objects, particles accelerated by a singularity's unfiltered fury. Others hunt for telltale flares in galactic centers, where a naked singularity's unshielded gravity might rip apart stars in uniquely violent ways. Yet for all the theoretical fireworks, the jury's still out. Penrose himself once bet against naked singularities existing in nature, a wager he later conceded might be too conservative. Meanwhile, white holes linger in the shadows, neither proven nor dismissed, keeping the door open to a universe far wilder than censorship would allow. Whether they're cosmic anarchists or just misunderstood outliers, one thing's clear. If white holes ever bear their singularities to the world, physics will never be the same. What if we could recreate the mind-bending physics of white holes right here on Earth? Not in the depths of space, but in a laboratory the size of a coffee table. Scientists are doing exactly that through analog gravity experiments, where carefully engineered systems mimic the extreme conditions around white holes and black holes using nothing more exotic than flowing water or ultra-cold atoms. These aren't just clever parlor tricks, they're revolutionary testbeds that let us probe quantum field theory in curved spacetime, a realm usually reserved for cosmic scales. Take fluid dynamics, for instance. In a landmark experiment, researchers created a white hole analog by channeling water through a narrow flume at precisely controlled speeds. When the water flows faster than the waves trying to move against it, something extraordinary happens. The waves hit a point where they can't make progress upstream, no matter how hard they try. This creates a hydraulic jump, a standing wall of turbulence that behaves just like a white hole's event horizon. Ripples approaching the barrier get stretched and amplified, mirroring how light would redshift near a real white hole in space. Even more strikingly, some experiments detected spontaneous wave generation at the boundary, an analog of Hawking radiation, the quantum glow predicted to emanate from black holes. Bose-Einstein condensates push the analogy even further. These ultra-cold clouds of atoms, chilled to within a whisper of absolute zero, can be tuned to exhibit space-time-like properties. By manipulating magnetic fields, physicists create flow patterns where certain regions become acoustically inescapable, precisely the conditions needed to simulate a white hole's repulsive gravity. In one groundbreaking study, researchers observed sound waves splitting into pairs at the simulated horizon, a direct signature of quantum particle creation. It's as if the condensate becomes a tiny universe, complete with its own relativistic effects playing out at a speed we can watch in real time. These experiments matter because they tackle one of physics' greatest challenges, merging quantum mechanics with general relativity. White holes in nature might be rare or even non-existent, but their lab-grown cousins let us stress test theories where math alone falls short. When fluid analogs reproduce Hawking radiation with stunning accuracy, it suggests the phenomenon isn't just a black hole quirk, but a universal feature of horizons. When Bose-Einstein condensates exhibit quantum entanglement across simulated spacetime boundaries, it hints at how information might escape real singularities. Of course, analog systems have limits. Water waves aren't truly relativistic, and condensates can't replicate the crushing densities of astrophysical white holes. But by distilling cosmic mysteries into tabletop experiments, scientists are uncovering principles that might govern the universe at its most extreme. Every ripple in a water tank, every quantum flicker in a supercooled cloud, brings us closer to answering whether white holes are hidden in the cosmos, or whether the cosmos itself operates like one vast, interconnected analog. Time travel isn't just the stuff of science fiction. It might be lurking in the equations of general relativity itself, and white holes could hold the key. Among the most dizzying possibilities is the idea of closed time-like curves, hypothetical pathways through space-time that loop back on themselves like a cosmic Möbius strip. If these curves exist, they'd allow for journeys into the past, with white holes potentially serving as the ultimate time machines. The connection comes straight from Kurt Gödel's groundbreaking solutions to Einstein's equations, which describe a universe so twisted by rotation that cause and effect tangle into knots. In such a reality, a white hole's eruption could forge a bridge between moments in time, stitching together events that should be separated by eons. Gödel's model presents a universe where the fabric of space-time isn't static but whirls like a vortex, dragging everything along with it. Under extreme conditions like those near a white hole, this dragging could become so severe that time itself coils into closed loops. Picture a spaceship orbiting a white hole in just the right way, riding the gravitational currents until it returns to its own launch date. The equations permit it, but the paradoxes pile up fast. What stops a time traveler from altering the past in ways that unravel their own existence? Enter the Novikov self-consistency principle, which acts like a cosmic editor, ensuring any actions taken in the past were always part of history. If you tried to, say, prevent your own birth, the universe would conspire to foil you, a glitch in the timeline smoothing itself out before it could fracture causality. Yet even this elegant safeguard has cracks. For one, Novikov's principle assumes a single, unchangeable timeline, but quantum mechanics suggests alternate realities might branch with every decision. Could white holes sidestep consistency by funneling travelers into parallel universes instead of their own past? Some models propose that the extreme space-time warping around a white hole singularity might momentarily open a gateway to such branches, offering a loophole in the rules. Others argue that the energy required to stabilize these curves would be so vast, even a white hole couldn't sustain it without collapsing back into a black hole. The debate reveals a deeper tension between relativity's playful geometry and quantum theory's stubborn randomness. Closed time-like curves might exist mathematically, but whether they're physically possible or whether white holes could ever power them remains one of physics' great open questions. For now, they serve as a thrilling reminder that the universe's rulebook might have chapters we've only begun to skim. Whether time travel is a hidden feature of reality or just a beautiful mirage in the equations, white holes keep the door tantalizingly ajar. String theory weaves a tapestry of the cosmos far stranger than anything in conventional physics, one where white holes might not just exist but emerge naturally from the geometry of hidden dimensions. At the heart of this idea lies the concept of compactification, the notion that our familiar four-dimensional universe is wrapped around tiny, curled-up dimensions too small to see. These extra dimensions aren't random. They fold into intricate shapes known as Calabi-Yau manifolds, which look like multi-dimensional origami under a mathematical microscope. And here's where it gets wild. Certain configurations of these manifolds could twist space-time so severely that they birth white holes as naturally as black holes form from collapsing stars. Imagine a Calabi-Yau shape with a peculiar kink or bottleneck in its structure. As strings, the fundamental vibrating threads of reality in this framework move through these regions, they could create gravitational effects unlike anything in our everyday experience. Some configurations might generate repulsive gravity, pushing matter outward instead of pulling it in. In essence, the manifold's geometry would act like a cosmic pressure valve, redirecting energy into an explosive outflow, a white hole in the making. The math suggests these wouldn't be rare flukes, but inevitable features in a landscape of possible universes. Brain-world scenarios take this even further. Picture our universe as a four-dimensional membrane, or brain, floating in a higher dimensional bulk. Collisions between brains could unleash titanic energies, warping space-time so violently that temporary white holes flicker into existence at the impact sites. These wouldn't be the eternal white holes of classical relativity, but ephemeral structures, cosmic sparks igniting and fading as dimensions rebound. Some models even suggest that the Big Bang itself could have been such a brain collision, with our universe erupting from a white hole-like explosion in the bulk. String theory also offers a potential escape from white holes' greatest hurdles. Take entropy. If white holes inherently reverse the arrow of time, how do they square with thermodynamics? String theory's holographic principle might hold the answer. Information trapped in a black hole could encode itself on the event horizon, then decode during a white hole's eruption, not as a reversal of time, but as a transfer of data between dimensions. It's as if the extra dimensions provide a backstage area where physics can rewrite its own rules without breaking the cosmic script. Yet for all its elegance, string theory's white holes remain elusive. No experiment has confirmed the existence of extra dimensions, let alone their twisted geometries. Critics argue this makes the whole idea untestable, a beautiful story with no verifiable chapters. But supporters counter that future gravitational wave detectors might catch echoes of Calobi-Yau vibrations or brain collisions, subtle fingerprints of a higher dimensional dance. Until then, string theory's white holes stand as a breathtaking reminder. If the universe has hidden layers, reality might be far richer and far weirder than we've dared to dream. Dark energy, the mysterious force accelerating the universe's expansion, might have an unexpected cosmic cousin, white holes. Both defy gravity's pull, one stretching space itself apart, the other ejecting matter with relentless force. Could there be a hidden link between these two enigmas? Some cosmologists dare to suggest that white holes aren't just exotic objects, they might be dark energy's explosive fingerprints, scattered across the fabric of space-time. The idea emerges from the peculiar symmetry of their behavior. Dark energy operates like an anti-gravity force, pushing galaxies apart on cosmic scales. White holes, in their purest form, do something similar, locally repelling matter outward with gravitational defiance. In quasi-steady-state cosmology, an alternative to the Big Bang model, the universe isn't born from a single explosion but continuously replenished by spontaneous energy creation. Here, white holes could act as cosmic pressure valves, releasing bursts of matter and energy to maintain equilibrium, their collective outflow mimicking dark energy's smooth influence. Picture trillions of microscopic white holes peppering the vacuum, each contributing a minuscule push to the universe's expansion like invisible springs embedded in space itself. But the theory stumbles on glaring challenges. For one, dark energy's distribution is perfectly uniform, while white holes would be discrete, localized events. How could their combined effect appear so seamless? Proponents speculate that if white holes existed in a quantum foam, a froth of virtual particles and microscopic spacetime fluctuations, their tiny, ceaseless eruptions might blend into a uniform repulsive force. It's akin to mistaking individual raindrops for a steady mist. From a distance, the discreteness vanishes. Critics pounce on the numbers. Dark energy accounts for 68% of the universe's energy budget, an enormous value to explain through white holes alone. Even if they existed in vast numbers, their energy output would need staggering fine-tuning to match observations. Worse, most white hole models predict violent, episodic outbursts, whereas dark energy's influence is whisper-quiet and constant. Some theorists counter that white holes could evolve over time, their initial fury fading into a more diffuse repulsion as the universe ages, like embers cooling from a fire. Quasi-steady-state cosmology adds another layer of controversy. While it elegantly sidesteps the Big Bang singularity by proposing continuous creation, it struggles to explain the cosmic microwave background's near-perfect uniformity or the precise ratios of light elements observed in the cosmos. If white holes were the engines of this creation, their eruptions would need to leave specific imprints patterns we've yet to detect. Yet the possibility lingers, a tantalizing what if at the intersection of relativity and quantum physics. If even a fraction of dark energy's push comes from white holes, it would revolutionize our understanding of cosmic expansion, not as a property of empty space, but as the collective sigh of countless quantum singularities breathing energy back into the void. Until we find proof, the idea remains a cosmic gamble that the universe's most elusive force might owe its existence to its most rebellious objects. What if singularities, those infinitely dense points at the heart of black holes, aren't real, but just mathematical mirages? Non-commutative geometry offers a radical answer, proposing that space-time itself has a fine-grained structure, like a fabric woven from indivisible threads. In this framework, the smooth continuum of Einstein's relativity dissolves into a quantum foam where coordinates no longer neatly commute, meaning measuring position and momentum in one order might give different results than the reverse. This tiny but profound tweak doesn't just tweak gravity's rules, it obliterates singularities entirely, replacing them with something far stranger: white holes. The magic lies in how non-commutative geometry treats extreme densities. In classical general relativity, a collapsing star's gravity becomes infinite at the singularity, shredding the equations into nonsense. But when space-time is granular, there's a built-in failsafe, a smallest possible scale where quantum effects kick in, preventing infinite collapse. Picture a collapsing star hitting this limit like a rubber ball compressing to its smallest possible volume before rebounding. The result, instead of a black hole's infinite pit, you get a quantum bounce, a momentary white hole eruption where space-time itself springs back outward. It's as if the universe has a cosmic trampoline woven into its fabric, catching collapsing matter at the last possible instant and flinging it back into existence. This flips traditional black hole thermodynamics on its head. Normally, entropy only increases, making white holes seem impossible. But non-commutative geometry suggests entropy could plateau at maximum density, then reset during the bounce, sidestepping the arrow of time's tyranny. Imagine a hard drive that, upon filling to capacity, doesn't crash but spontaneously reformats itself. White holes might be nature's way of hitting the cosmic reset button. Observationally, the differences are stark. Classical relativity predicts black holes as eternal traps, while non-commutative models imply they're temporary way stations. If correct, we might spot dying black holes flickering into white holes through unusual bursts of high-energy particles or gravitational waves with telltale echoes from the quantum bounce. Some theorists even suggest that fast radio bursts, those mysterious millisecond flashes from deep space, could be white hole signatures, their brevity hinting at the Planck scale instantaneity of the rebound. Yet challenges remain. Non-commutative geometry's predictions often blur into quantum gravity's uncharted territory where experiments struggle to tread. And without direct evidence of space-time's granularity, white holes in this model remain tantalizing what-ifs. But as gravitational wave astronomy sharpens its lenses and quantum simulators grow more sophisticated, we might soon glimpse whether singularities are truly the universe's dead ends, or just cosmic cul-de-sacs with white holes waiting on the other side. The answer could rewrite not just our maps of black holes, but the very definition of reality's building blocks. What if the universe didn't begin with a bang, but with a quantum whisper, a spontaneous flicker from absolute nothingness into existence? This is the heart of the no-boundary proposal, a daring idea from James Hartle and Stephen Hawking that reimagines the Big Bang not as an explosive origin, but as a smooth mathematical transition from nothing to something. And buried in their equations lies a startling possibility. White holes might be the cosmic fingerprints of this quantum leap, tunneling events where reality bubbles up from the void like a cosmic souffle rising in an oven. The no-boundary proposal ditches the traditional idea of a singularity, a point of infinite density where physics breaks down, and replaces it with a four-dimensional sphere, a geometry where time and space curve back on themselves like the surface of a ball. There's no sharp edge, no starting gun, just a gradual emergence from quantum fuzziness into the universe we recognize. This isn't just poetic imagery, it's grounded in something called Euclidean quantum gravity, where time temporarily becomes imaginary in the mathematical sense to sidestep singularities. Picture a river flowing uphill for a brief stretch before cascading back down, except here, the river is space-time itself, and the uphill flow is a quantum fluctuation birthing reality. Where do white holes fit in? If the universe tunneled into existence from nothing, could individual regions of space-time do the same on smaller scales? Some interpretations suggest that white holes might be local versions of the no-boundary process, miniature cosmic births punctuating the fabric of reality. Instead of matter collapsing into a black hole singularity, it could quantum tunnel through impossibly dense states and re-emerge as a white hole, like a ball phasing through a wall in a quantum mechanics thought experiment. The math even hints that these white holes wouldn't have a before, they'd simply blink into being already mid-eruption, as if the universe had pressed play halfway through the scene. But here's the catch: testability. The no-boundary proposal unfolds at energies so extreme and scales so tiny, it's like trying to detect a single raindrop in a hurricane. Hawking himself admitted that confirming the idea might be impossible with current technology, yet glimmers of hope exist. If white holes are indeed quantum tunneling events, they might leave subtle statistical clues in the cosmic microwave background, anomalies in temperature fluctuations or polarization patterns that betray their presence. Others look to gravitational wave observatories, hoping to catch echoes of a white hole's birth encoded in the ripples of space-time. Even if we never observe them directly, their theoretical existence reshapes how we think about the universe's origins. Are singularities truly unavoidable or just artifacts of incomplete physics? Does time always flow forward, or is the arrow reversible at quantum scales? The no-boundary proposal doesn't just challenge our cosmic origin story, it questions whether origin even makes sense in a universe where time can loop, tunnel, or dissolve entirely. White holes, in this light, aren't just cosmic oddities, they're stress tests for reality itself, probing whether the universe plays by rules we've only begun to glimpse. Whether they are out there or not, their possibility forces us to confront a humbling truth, that the boundary between nothing and something might be far stranger and far more porous than we ever imagined. Eric Verland's radical theory of emergent gravity turns our understanding of the universe on its head. What if gravity isn't a fundamental force at all, but an illusion, a side effect of something far deeper? His framework suggests that gravity emerges from the way information and entropy intertwine at cosmic scales, like heat rising from the motion of atoms. And in this strange new worldview, white holes might not just be oddities, they could be entropy's rebellious offspring, regions where the usual gravitational script flips upside down. At the heart of emergent gravity lies a startling claim. What we perceive as gravity is actually entropy's way of optimizing information. Picture the universe as a vast, shifting network of microscopic bits, like a cosmic computer constantly rearranging its memory. When matter disturbs this network, the system responds by maximizing entropy, creating what we feel as gravitational attraction. It's as if space itself has a kind of elasticity, stretching and deforming to keep information in balance. But what happens when this cosmic optimization hits a snag? That's where white holes come in. If black holes are regions where entropy soaks up information like a sponge, white holes could be the opposite points where entropy spontaneously unwinds, ejecting information back into the universe like a coiled spring suddenly released. This flips dark matter's role on its head. In standard cosmology, dark matter's gravity holds galaxies together. But in Verland's model, the extra gravitational pull comes from entropy gradients in the underlying information fabric. No exotic particles required. Now imagine white holes as glitches in this fabric, temporary ruptures where entropy's flow reverses. Their repulsive gravity wouldn't just defy Newton and Einstein, it could mimic dark matter's effects in unexpected ways. For instance, if white holes clustered at galactic edges, their outward push might offset the need for dark matter's invisible halo, explaining why stars at a galaxy's outskirts rotate faster than predicted. Critics are quick to point out gaps. Verland's equations struggle to match all galactic observations, and white holes as entropy reversals remain speculative. Yet the possibility lingers that what we call dark matter might actually be the shadow of something far stranger, a universe where gravity is a hologram and white holes are the ripples in its projection. Whether this vision holds up or not, it forces us to confront a profound question. Are we mistaking the universe's subtle programming for invisible substance? The answer could rewrite not just our maps of the cosmos, but our understanding of reality itself. What if white holes aren't objects at all, but cosmic projections, holographic screens displaying information from a reality we can't see? The holographic principle, one of the most mind-bending ideas in physics, suggests our three-dimensional universe might be a shadow cast by data encoded on a distant two-dimensional surface. Like a movie playing on a flat screen that somehow feels immersive, every star, galaxy, and even your own hands could be pixels in a vast cosmic projection. Now take that logic and apply it to white holes. Instead of physical objects spewing matter into space, they might be glitches in the projection points where higher dimensional data bleeds through, rewriting the rules of our reality in real time. At the heart of this idea lies a radical reimagining of space-time itself. In the holographic framework, the information that makes up a black hole isn't lost when it swallows matter. It's smeared across its event horizon like ink on a page. Flip the script and a white hole becomes that information playing back in reverse, not as a physical eruption but as a reconstruction, a data stream decoding itself into the illusion of matter and energy. Picture a DVD scratched just enough to skip scenes, except here, the scenes are chunks of space-time and the skip is a white hole's violent outburst. The holographic principle doesn't just allow for this, it might demand it, as a way to preserve cosmic information integrity. The implications ripple through our understanding of reality. If white holes are holograms, their explosions aren't just ejecting particles, they're rendering pixels, rebuilding lost data from some deeper layer of existence. This could solve one of physics' stickiest problems, how information escapes a black hole's grip. Instead of tunneling through space, it's simply recalculated elsewhere, like a corrupted file restored from backup. Even stranger, holographic white holes might not exist in the traditional sense. They'd be ephemeral artifacts, like a glitch in a video game that spawns objects from nowhere before the system corrects itself. Critics argue this stretches the holographic principle into untested territory. After all, we've yet to prove our universe is truly a hologram, let alone that white holes are its debugging tools. But supporters counter that certain quantum gravity models predict just this behavior, that singularities aren't physical endpoints but computational bottlenecks, where the universe's processor hits overflow and reboots via white hole-like resets. Whether this vision holds up or not, it forces us to ask, if reality is a projection, what's projecting it? And are white holes the universe's way of editing the script on the fly? The answers might lie not in telescopes, but in the quantum codes underpinning existence itself. Roger Penrose's conformal cyclic cosmology paints a picture of the universe far grander than a single Big Bang, an endless cycle of eons, each ending in heat death before reborn through white holes acting as cosmic seamstresses. In this daring model, the distant future of our universe doesn't fade into eternal darkness, but transforms into the Big Bang of the next. The key lies in conformal rescaling, a mathematical trick where an infinitely expanded, cold universe can be rewound to appear identical to an infinitely dense, hot singularity. Imagine zooming out on a snowflake until it becomes a featureless point, then zooming back in to find it's now the seed of an entirely new crystal. That's CCC in a nutshell. White holes stitch the fabric of one eon's death to the next birth. The mechanism hinges on Hawking radiation's slow evaporation of black holes over eons. As the last supermassive black holes dissolve, they release all trapped information into a universe now devoid of matter, leaving only photons drifting endlessly. At this point, Penrose proposes something extraordinary. The stretched-out, low-energy photons from these evaporations become mathematically indistinguishable from the high-energy particles of a Big Bang when rescaling is applied. White holes emerge as the bridges between these phases, not as explosive events in space, but as natural geometric transitions where one eon's causal structure smoothly feeds into the next. It's as if the universe presses a cosmic reset button not by collapsing, but by reinterpreting its own emptiness as a new beginning. The most tantalizing evidence comes from so-called Hawking points, strange, circular patches of unusually warm spots in the cosmic microwave background. Penrose argues these are the imprints of supermassive black holes from the previous eon. Their final Hawking radiation bursts etched onto our sky like shadows from a forgotten universe. If true, each point marks where a white hole's influence subtly warped our cosmos' birth. Critics counter that these anomalies could just be statistical flukes, but the sheer number of matching patterns, some with temperature deviations precisely where CCC predicts, keeps the debate alive. This radical vision redefines white holes' role entirely. They're no longer isolated oddities, but the universe's recycling system, cosmic tendrils threading through infinity, ensuring information never vanishes, only transforms. Whether CCC withstands scrutiny or not, it forces us to confront a breathtaking possibility, that our universe's birth wasn't a beginning at all, but a continuation, with white holes as the hidden stitches in time's endless tapestry. Quantum mechanics tells us particles can exist in multiple states at once until something forces them to choose. This mysterious transition from fuzzy superposition to definite reality is called decoherence, and white holes might be playing a hidden role in the process. Imagine a quantum particle teetering between possibilities, its wave function spread across probabilities like ripples in a pond. Normally, interaction with the environment, a stray photon, a passing atom, collapses those possibilities into one outcome. But what if some cosmic-scale objects act as ultimate decoherence machines, draining quantum ambiguity from the universe like a sink pulls water down a drain? That's the provocative idea behind white holes as decoherence sinks, where the fabric of space-time itself might terminate superpositions in ways we've yet to understand. At the heart of this theory lies a marriage between relativity's most rebellious objects and quantum mechanics' deepest puzzles. The Gerardi-Rimini-Weber GW theory, one of the leading alternatives to traditional wave-function collapse, proposes that superpositions spontaneously localize over time not through observation, but via an inherent flicker in reality's fabric. Now picture a white hole's explosive boundary as a GRW hotspot, where space-time's extreme curvature acts like a quantum pinball machine, violently knocking particles into definite states. Unlike gentle environmental decoherence, this would be collapse by cosmic sledgehammer, a region where the universe's simmering quantum soup boils over into classical certainty. The math hints at eerie possibilities. A white hole's repulsive gravity could scramble quantum correlations across vast distances, severing entanglement like scissors cutting tangled strings. Particles passing near its horizon might experience accelerated decoherence, their wave-like properties crumbling faster than thermodynamics predicts. Some models even suggest that white holes could trap superposition states beyond their boundaries, effectively acting as cosmic erasers for quantum ambiguity. It's as if the universe has designated these regions as no-fly zones for maybe where probabilities go to die. Critics raise valid concerns. If white holes' collapse wave functions so efficiently, why haven't we detected anomalous decoherence patterns near suspected cosmic explosions? Proponents counter that primordial white holes could be hidden in plain sight, their decoherence effects masked by the quantum noise of the early universe. Others suggest that supermassive white holes might influence quantum behavior only at scales too vast for current labs to measure, like tidal forces too subtle to notice in a teacup but undeniable in an ocean. The implications ripple through foundational physics. If white holes actively prune quantum branches, they might explain why the macroscopic world feels so solid while the quantum realm remains fluid. They could even reshape interpretations of measurement itself, not as human intervention, but as gravitational inevitability. Whether this theory holds up or not, it offers a breathtaking vision that the universe's most defiant objects might also be its ultimate arbiters of reality, cosmic judges presiding over the transition from possibility to fact. In a quantum universe brimming with maybes, white holes could be the hammer that nails down what is. Einstein's general relativity isn't the only way to explain gravity's grip on the cosmos. What if the secret to white holes lies not in the curvature of space-time but in its twist? Enter teleparallel gravity, a radical alternative where torsion, not curvature, takes center stage. Here, white holes aren't just time-reversed oddities. They're natural byproducts of space-time's hidden spirals, cosmic whirlpools where gravity itself flips inside out. At its core, teleparallel gravity reimagines gravity's engine. Instead of matter bending space-time into hills and valleys, it's torsion, a kind of microscopic corkscrew motion in the fabric of reality that dictates how objects move. Picture space not as a trampoline sagging under weights, but as a lattice of interconnected gears, each turn transmitting force through rotation. In this framework, black holes emerge where torsion coils space-time into an inescapable spiral, while white holes are the recoil, the snap back when torsion unwinds, violently repelling matter outward like a spring released. It's a cosmic seesaw, where general relativity gives us warped geometry. Teleparallel gravity offers torque, trading Einstein's curved canvas for a dynamic, twisting scaffold. The implications for cosmology are profound. Torsion doesn't just avoid singularities, those pesky infinities where physics breaks down, it erases them entirely. A collapsing star in teleparallel gravity hits a point where torsion resists further tightening, then rebounds. No infinite density, no information loss, just a smooth transition from black hole to white hole, as natural as a pendulum swinging back. Some models even suggest torsion could explain dark energy's repulsive force, with white holes acting as local outbursts of the same anti-gravity effect driving the universe's expansion. Compare that to general relativity, where dark energy is tacked on as a cosmological constant, an ad hoc fix with no deeper origin, yet challenges remain. Teleparallel gravity struggles to match general relativity's precision in predicting planetary orbits or gravitational lensing. Critics argue it's a mathematical curiosity, lacking the experimental validation Einstein's theory enjoys. But supporters point to subtle signatures. Torsion might leave in gravitational waves unique spiraling patterns that detectors like LIGO could one day spot. And if white holes are torsion's fingerprints, their eruptions might carry telltale twists in polarized light or particle jets, clues that gravity's true language is written in helices, not parabolas. The debate reveals a deeper tension in physics. Is the universe a geometric masterpiece or a kinetic sculpture? General relativity paints gravity as a static landscape, while teleparallel gravity recasts it as a dynamic dance. White holes, in this light, become more than theoretical outliers. They're stress tests for competing visions of reality. If torsion shapes the cosmos, then every black hole's death might birth a white hole not by reversing time, but by unwinding space itself, a cosmic reset powered by the universe's hidden spin. Whether this vision holds up or not, it reminds us that gravity's story is far from finished, and the strangest chapters may still be waiting to be written. What if white holes aren't cosmic objects at all, but errors in the universe's source code? The simulation hypothesis, the idea that our reality might be an advanced computational construct, throws a radical twist into the white hole mystery. If the universe runs on quantum algorithms, these theoretical eruptions could be nothing more than bugs in the system overflow errors or corrupted memory addresses where the simulation struggles to reconcile its own rules. Picture a video game glitching when too many particles collide at once, spawning objects from nowhere or warping physics momentarily. White holes might be the universe's equivalent, patches where the program fails to render gravity correctly, spitting out matter instead of swallowing it. The logic follows from the simulation argument's core premise. If an advanced civilization built our reality as a numerical model, it would need to conserve computational resources. Black holes could function as cosmic garbage collectors, compressing data to save memory. But what happens when the system encounters an edge case, a calculation so extreme it crashes the subroutine? A white hole might be the result, the simulation's desperate reboot, a buffer dump spewing back mangled data in the form of energy and particles. Some theorists even suggest that gamma-ray bursts could be the pixelated artifacts of these crashes, their unnatural energy signatures betraying the limits of the universe's rendering engine. Critics, however, pounce on a glaring flaw: falsifiability. For all its poetic appeal, the simulation hypothesis borders on metaphysics. How could we ever prove white holes are glitches rather than natural phenomena? Proponents counter that certain anomalies, like particles appearing to violate conservation laws or energy levels aligning suspiciously with computational thresholds, might hint at underlying code. If white holes exhibit behavior that defies standard physics in mathematically elegant ways, like error-correcting sequences or pixelation patterns in their radiation, that could be the smoking gun. But the debate runs deeper than observational quirks. If white holes are simulation artifacts, they challenge the very definition of scientific inquiry. Science relies on natural laws being consistent and discoverable, but if those laws can be patched or debugged by unseen programmers, predictability collapses. It's the ultimate cosmic conspiracy theory that the universe's rulebook isn't fixed, just occasionally buggy. Philosophers like Nick Bostrom argue this isn't inherently unscientific, just uncomfortably meta. After all, glitches in a simulated universe would still follow higher-level rules, even if those rules are someone else's design choices. Yet the hypothesis dangles one tantalizing possibility. If white holes are artifacts, their existence might inadvertently reveal the simulation's resolution limits, like finding the jagged edges of a digital image when zoomed in too far. Quantum foam, the frothy turbulence of space-time at microscopic scales, could be the universe's equivalent of pixel grain. White holes erupting from this foam might carry imprints of their algorithmic origins, like a corrupted file still bearing traces of its original code. Whether this theory holds water or not, it forces a profound reevaluation of white holes' significance. They might not just be oddities of gravity or time, they could be cosmic breadcrumbs, hinting that reality is far stranger and far more malleable than we ever dared to imagine. In the end, the question isn't just whether white holes exist, but what their existence would say about the very nature of our universe, real or rendered. From the mathematical elegance of time-reversed black holes to the holographic glitches rewriting reality's code, white holes have taken us on a tour through physics' most daring frontiers. We've seen them emerge as quantum saviors rescuing information from oblivion, as dark matter imposters hiding in plain sight, even as cosmic stitches sewing together infinite universes. Some theories paint them as fleeting quantum hiccups, others as Planck-scale trampolines bouncing dying stars back into existence. They've tormented us with naked singularities, tempted us with time loops, and dared us to question whether the universe itself might be a simulation glitching out. What's astonishing isn't just the variety of these ideas, it's how each one stretches our understanding of space, time, and existence to the breaking point. White holes aren't just cosmic oddities, they're stress tests for every major theory in physics, from general relativity to quantum gravity. They force us to ask uncomfortable questions. Can entropy ever run backward? Is information truly immortal? Does causality bend or break under extreme conditions? Every hypothetical white hole is a mirror held up to our assumptions, revealing cracks we never knew were there. Yet for all their theoretical fireworks, white holes remain elusive. No telescope has caught one erupting, no detector has recorded their gravitational whispers. This absence isn't failure, it's an invitation. Every unanswered question is a challenge to the next generation of physicists, astronomers, and dreamers. Maybe the key lies in a futuristic lab simulating quantum black holes, or in reanalyzing decades-old gamma-ray burst data with fresh eyes. Or perhaps the real breakthrough will come from someone watching this video right now, connecting dots no one else has seen. So here's where we turn the microphone to you. Which white hole theory left your brain spinning? Was it the holographic universe's pixelated rebirths, the baby universes sprouting inside black holes, or the chilling possibility that we're all living in a cosmic simulation's debug mode? Drop your favorites in the comments. We'll be diving into the wildest responses in future videos. And if you're hungry for more mysteries that bend the laws of reality, hit subscribe. From wormholes to dark energy, the universe has infinite surprises left to unpack, and we're just getting started.